also working in NIO, National Institute of Ocean and Geophysics.
Really?
They also do some work of maybe remotely connected with engineering. Well, formally, good morning to all of you again. I'll try to speak as loudly as possible. Mainly, I would encourage you to stop me anywhere, anytime. So it's not really a very formal in that sense. I'll try to talk about this activity here, computational acoustics. I would just tell you up front that we belong to a school of thought which does not distinguish that you'll have to have so-called horses for the courses. Instead, what we are trying to do is give you in a general framework computing methodology which will be more or less ready for multi-physics applications. So in a sense, I am going to tell you that if you want to do acoustics, you can have a high accuracy fluid dynamics code that will give you simultaneously fluid flow properties as well as acoustic properties. And this will be done under the framework of what is called as large eddy simulation or direct numerical simulation. So this will be somewhat different. So I just begin with this opening remark. As I told you, there is a unity that we want to talk about scientific computing of fluid flow and acoustics. Both of it requires high accuracy. Why? Well, when I'm talking about it requires high accuracy, I'm talking about this quantity, small dissipation that is always associated with fluid flow. If you compare computational fluid dynamics with computational structural dynamics, the answer is very apparent. Why? Because for structural dynamics, you have coefficient of friction or dissipation is of the order of 10 to the power minus 2, even if we are talking about rolling friction, right? Static friction is 10 times more. Whereas in fluid mechanics, what you have is a coefficient of friction or dynamic viscosity, as we call it, is of the order of 10 to the power minus 5. So the fact that you have to solve a problem which has lower dissipation makes the subject rather interesting. Because if you are doing structural dynamics, you'll be happy to get 3 modes, 5 modes, and you say, oh, I have all the mode shapes and everything will be fine, right? But when it comes to fluid mechanics of high Reynolds numbers of interest, you would notice 5 modes will hardly ever capture, sometimes even 80% of energy or entropy. I would talk about the distinction between modes and energies and entropies in a detailed way later, but you got to understand that the small dissipation is small for fluid flow makes it rather interesting, because you require more degrees of freedom to describe the flow, and it's a challenge. That's what you have to understand. So that's what we are talking about. You have fluid flows having higher dimensionality as compared to computational, say, structural dynamics, which is the other branch of continuum mechanics. And of course, whenever we are in trouble, we look for excuses. So the culprits are nonlinearity, complexity, chaotic nature, etc., etc. We have a lot of adjectives to do. Tell you what, if you can solve your problem in the linear framework quite accurately and correctly, these are additional spices. They make life a little more pleasant rather than a problem. I would point it out to you. However, I must tell you that we still haven't come to a stage where we can answer that million-dollar question. That what we are looking at when we are trying to compute. Are we looking at a deterministic system, or are we looking at a stochastic system? Okay? Like, simple example, tossing a coin. Will we be able to solve it as a mathematics problem, computational problem? What is the general consensus? Tossing a coin. Can we just predict the outcome? All of you are saying no. Otherwise, that first 5 minutes of IPL telecast will be gone. A lot of fun. Tossing a coin. In fact, interesting bit is all of our sports activity depends on stochastic nature of fluid flow. If the cricket ball trajectory is known, and I know the dynamics, how the bat hits the ball, then I should be able to solve